But I would say the ABWR is sort of a really, really beautiful design process that occurred. GE brought in Hitachi, Toshiba, GE, of course, and the Swedes and the Italians all into a single design group to figure out what is the best operating experience, what is the best design elements that we can take out of the Swedish and US and Japanese nuclear fleet. That design was able to have nuclear construction done in 38 months in Japan at Kashiwazaki Karya Unit Number 6. And we basically built a 1.35 gigawatt plant in less than 4 years of nuclear construction, which is extraordinary. In my mind, the world would be a much better place if, rather than Vogtle Unit 3 and Unit 4 being a AP-1000, it would be an ABWR.
A warm welcome back to Decouple. Today, I'm joined by returning guest. I don't know how many we have in the catalog, James, but yes, it is the one and only James Krellenstein. We've got a very special episode for you today. We're going to deep dive the Better Water Reactor. But before I do, we get new listeners tuning in all the time. So for those of you who don't know James, he had a nuclear power childhood, celebrated his, I think, 6th or 7th birthday in a nuclear power plant.
Indeed.
Which violates tons of NRC statutes that James could list off encyclopedically, no doubt. James was or is maybe a North Korea expert. He blew up his high school chemistry laboratory.
Don't put that
He's
in
a
there,
physicist. I got to get rid of that. Can we leave it? I think it's cool.
Okay, whatever. Keep that in.
All right. Anyway, I'm going on and on. But
yeah, my name is James, and we can leave it at that.
Fine. Boiling water reactors. That's what we're going to talk about today.
I'm the CEO of Alva Energy, which is a startup looking at in the pressurized water reactor uprate space. But let's go deep into BWRs. Very different than what we're talking about now.
Wonderful. Yeah. So BWRs are a little bit of an enigma to me. We had a great episode on the 3 Mile Island accident where you, I think, communicated very well how PWRs work and sometimes don't work. But it was a great orientation. So if folks want to kind of get their heads around PWRs, head over there. We're going to take a different approach today. But as I was saying, BWRs, a little bit of an enigma to me. There's a lot of differences. I mean, obviously, water is the moderator, water is the coolant, but some big changes. So today I want to talk about
light water.
Light water, yes.
So there are have been some heavy water boiling water reactors, right?
We did one, but let's not
sully
pollute everything with heavy water and can do talk. In any case, I want to know the why, I want to know the when, the how, the where. This is the second most widely deployed reactor, but it competes or even outcompetes PWRs. I'm just fascinated. There's such different engineering approaches, but they both kind of end up with similar LCOE, similar capacity factors. It's a really cool story. So, James, I'll let you sort of take it away wherever you want to start it.
So BWRs, on the most basic difference here, the difference is in the name, right? In a pressurized water reactor, the water that we run through the reactor itself, what we call the reactor coolant system, is under immense pressure. So even though it gets to very high temperatures, above 300 degrees Celsius, it never goes through any sort of bulk boiling. There's never any steam, ideally, in the primary circuit of water in a pressurized water reactor. That is the water that's moving through the reactor. In a boiling water reactor, as its name implies, we boil the water directly in the reactor pressure vessel. And we actually, rather than having a separate steam generator and a whole separate loop of water, we literally boil the water in the reactor and we get steam, and that steam goes directly to the turbine, expands in the turbine, does its work to turn the generator, then gets condensed and gets returned as feed water directly to the reactor, obviously through some feed water heating and so on. So this is a dramatic difference. We've eliminated an entire loop out of the PWRs and just are literally doing a direct cycle, boiling the water, running the reactor coolant through the turbine, condensing it, and returning it right back. That's the primary difference. And part of that is that there's dramatic actually differences in how the actual nuclear reaction, the fission reaction, actually takes place in a BWR versus a PWR, right? And as you noted at the beginning, in both a PWR and a BWR, water is the moderator of the neutrons. And what a moderator means is that the hydrogen atoms on the water molecules essentially work to slow down the neutrons. When the neutrons come out of the nuclear fission reaction, right? When, once again, in a nuclear reactor, what we're doing is we're taking a neutron that's hitting uranium-235 or a plutonium atom, and that's splitting and yielding secondary neutrons that then ideally hit other nuclei and continue the chain reaction. But in order to basically increase the probability that those neutrons actually successfully hit a target nuclei and actually induce that nuclei to fission, we actually want to slow down the neutrons, right, to increase the probability or the cross section of those uranium and plutonium atoms that they want to hit. And that's what in a thermal reactor we call a moderator, right? That's a thing that literally is slowing down those neutrons, and that's water here in both the BWR and PWR. But the fundamental issue here, if you want to go into this, is that when you have boiling, as anyone who's ever made a pot of pasta knows, you have bubbles. And those bubbles we can sometimes call voids. And the reason why we call that is because the density of steam is 100-fold lower than the density of liquid water. So you think about this from the perspective of a neutron that is coming out of a fission reaction at a very, very high speed. In a pressurized water reactor, there's just liquid water as far as the eye can see. But in a BWR, there's both liquid water and there's steam bubbles that are a product of the boiling. And when that neutron hits a steam bubble, there's literally 100 less water molecules, roughly speaking, per unit volume than there is in liquid water. So the actual amount of moderation that occurs in that bubble is dramatically lower. So we get a really interesting dynamic here. More bubbles mean less moderation, which means less reactor power. Less bubbles mean more moderation and more reactor power. So I kind of just dove right in there.
No, that's good. But yeah, let's explore that further. But first off, where did the interest come from? We had the PWR developed primarily for naval propulsion, first in submarines, later aircraft carriers, then turned into a shipping port. Where did this interest come in? Was it just, hey, we could eliminate a whole secondary loop? This would be simpler, cheaper. Was it just sort of exploring all the different potentials within nuclear alongside, different reactor concepts in the illustrious 1950s, or what was going on?
Two basic questions. This is totally a product of government research at actually Argonne National Laboratory and what we called the National Reactor Test Station, which is now Idaho National Lab in Idaho. And it was led by Walter Zinn, who is the father of most reactor designs that we talk about today, as well as including Chicago Pile 1 with Fermi, and a guy named Samuel Untermeyer II. And Untermeyer had this question about, could a boiling water reactor actually be stable? And let's figure out why there was that question. And not going into too deep of reactor physics or thermal hydraulics, the question is actually pretty easy to understand why it's a question. What I said before, the bubbles basically make reactor power go down. More bubble or void fraction, as it's called, decreases the amount of moderation, which decreases reactor power. Now you can imagine a pretty easy instability that can emerge here, because it's almost like you're changing the dial on your stove when you're boiling a pot of water. When you see a lot of bubbles, you turn the temperature of the stove down, which means that there'll be less bubbles. But then when there are less bubbles, you turn the stove back on. The same thing is kind of going here in a boiling water reactor, or could be. You can imagine that as we increase reactor power, right, we start creating more and more bubbles, right? Because there's more and more heat being generated, which means, of course, there's more water boiling and therefore more bubbles. But at that point, that actually decreases reactor power, which means that there are going to be less bubbles and more liquid water, which is going to increase reactor power. So you could imagine that there's a regime in which you could literally get into these power oscillations, where in fact you are creating more bubbles, that's decreasing reactor power. Great. But then all of a sudden you have more liquid water, which increases reactor power, and you go back and forth, back and forth, back and forth. And what these BORAX experiments, and there's BORAX 1 through 5, right, was to show that actually there are certain areas of power and core recirculation flow, or even just natural circulation through the reactor, that allow the sort of reactor to reach a sort of happy, stable medium where the reactor power is really stable. The actual bubble generation is at equilibrium with the amount of reactor power. And so that you actually stabilize the power. But this was a really open question in the late 40s and early 50s. So given that there was very limited computing capacity, given that all the thermal hydraulic and all the sort of thermal correlations that we have now weren't really generated at that point, in the sort of heyday of 1940s, 1950s America, we just built these experiments.
It's a cool experiment. We will link it in the videos, but there's a great, I'm not sure if it's Department of Energy or Atomic Energy Commission, I guess at the time, video.
Atomic Energy Commission.
This is this like basically embedded reactor pressure vessel, a kind of open pool though, with your control rods hanging out the top, an earth embankment, and then there's a mirror, and it sort of shines down into this open pool. And when they pulse the power, I mean, it's extraordinary. This thing comes to a boil in microseconds, and they remove control rods faster and faster, and finally they blow the whole thing up. And there's bits of reactor scattered 200 meters, around in the desert. And the voiceover is saying, "Hey, not really any big fallout issues, just chunks of, fuel elements here and there." It's a wild video.
We really did blow up one of the BORAX reactors, and as you said, it's on video. It's a fun video to watch, and we did blow nuclear fuel, a very, very low burn up, so the amount of actually source term there is very, very small, right, relatively speaking. But I don't think we're going to be blowing up any reactor anytime soon, unfortunately, in today's world. But it did also show, though, this sort of self-moderating ability that even when we eject a rod, you can have a power transient, but that flashing of reactor coolant in the actual reactor really does promptly decrease reactor power. And so even though we exploded the reactor, it did sort of demonstrate a proof of concept that there is an inherent sort of break that is pretty profound and pretty dramatic in a BWR that prevents really extreme, or in most cases can prevent really extreme positive reactivity excursions or power transients. And this is a great thing. And the other thing that really you realize here is that BWRs rather uniquely can control reactor power just by changing the amount of water that we're recirculating through the core. And in a commercial force circulating boiling water reactor, which is actually all the operating BWRs right now, reactor power above a certain point can be fully controlled just by changing the amount of water that we swoosh through the core, literally swishing those bubbles away from the nuclear fuel and increasing the amount of liquid water, thereby decreasing the void fraction and increasing the amount of moderation of the neutrons, increasing reactor power, which is a really cool aspect of a BWR.
So far, you've described this kind of primary loop. I described the BORAX experiment, which again looks like kind of an open pool reactor. People have probably seen those videos of trigger reactors where you can see the Trenkov flash. And again, watch this video. We'll link it in the show notes, because instead of a Trenkov flash, the water just boils and slurges out like magma or like a volcano. It's really extraordinary. But let's get a little bit deeper into again, what makes it different. BORAX, obviously there's no power conversion system on it.
Well, BORAX 3, there was the first steam turbine and generator, and actually the first town that ever got powered by nuclear energy, Arco, Idaho, was of course powered by BORAX 3, right? By that 500 kilowatt generator. I believe it's 500 kilowatts. I think 2,000 kilowatts thermal. And actually that was the first real commercial scale. EBR2 did like 6 light bulbs, but BORAX 3 with a steam turbine and generator really actually powered a town in the U.S. in 1955, July 17th.
So there's some weird things though in terms of how the reactor pressure vessel is put together, because you have an airspace inside of your reactor pressure vessel, which you don't have in a PWR. You got to take a bunch of steam and do something with it, right? So control rod position, there's a whole bunch of weird stuff. So just walk us through that quickly, just to better orient people again.
The first thing is, if you look at a BWR reactor pressure vessel, it looks upside down, right? The control rods come in from the bottom rather than from the top, and there's two reasons for this. One is that from a neutronics perspective, the highest reactivity portion generally of a BWR, the peaking is generally at the bottom of the core, usually, not always, but it is because there's the most amount of liquid water. There's the least amount of steam actually at the bottom of the core. So in some ways, the bottom of the core is most reactive. So when you're trying to scram a reactor, you want to have the control rods go up to the most reactive portion quickly. And actually, the Chernobyl reactors, which are actually boiling water reactors, not water moderated, but actually have boiling happen in the core. One of the actual challenges there is the control rods came from the top, and actually that sort of reactivity difference actually really was quite profound and different. Although, once again, we're inverted here because they have a positive void coefficient rather than a negative void coefficient. But anyway, so I don't want to get distracted on RBMKs there. But one of the things that is really clear is that BWRs have very, 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 very prompt negative void coefficients, very dramatic negative void coefficients. And unlike a PWR, they're voiding, right? By design, if you're voiding in a PWR, you're generally in a very serious accident if you're having a lot of actual bulk boiling happen in the pressurized water reactor. But the other thing, the key is a boiling water reactor is much taller than the reactor pressure vessel is than a PWR. And that's both because we have generally actually sometimes we have a slightly taller core sometimes, but mainly it's because we have a full steam dryer assembly above and a chimney right above the actual reactor core inside the reactor pressure vessel. It's like almost like you mixed a steam generator in with a reactor pressure vessel, right, into one sort of single thing, which is great from a modularity and actually increasing a lot of the sort of simplification of the system. We're putting almost all of it in the reactor. So basically what you have is you have feed water lines coming in, which are dumping liquid water in, and you have steam lines at the top of the RPV that are just taking the reactor steam and sending it out through the containment into the turbine building and to the turbine, obviously, to make power. So the other thing that we have generally a lot is some sort of way to recirculate the water in a boiling water reactor, right? Generally, as I said before, if you want to get to a high power density inside a boiling water reactor, we really do need to recirculate. That is not just take the feed water, take the steam out, condense it, return it back as feed water, but just literally take water inside the reactor and kind of recirculate it. And generally recirculation flows are about 4 times, and sometimes even higher than that, than the amount of feed water and steam that's coming in, just because the amount of reactor power is so intricately coupled to the actual amount of recirculation flow. So in the first BWR product lines, we actually had in the commercial BWRs from General Electric. Well, we're getting a little ahead of ourselves because we just started with BORAX, and we have to go to the evolution of how these reactors became commercial and why, as you noted, they weren't taken up by the Navy at all.
Right. So just before we do that, a couple, I think, very basic kind of questions and comments. I was looking at some 3D mock-ups of BWR RPVs. One question is, I mean, and this applies to PWRs as well, probably, but especially with these control blades coming in from the bottom and reactor pressure vessels needing to be pretty tightly sealed, like, are there O-rings or there's all these holes right in the bottom of the RPV where these the control blades are coming in, and just how do they not leak? Like, just in terms of you've got something moving up and down through a perforation at the bottom of your RPV. I'm sure this is a basic materials engineering question, but I'm just curious.
I mean, they have they have very complex sealing systems. I wouldn't argue that. Remember, a BWR pressure is about half of what the pressure of a pressurized water reactor is. Right, because the BWR pressure is basically at as a close to basically what the steam line pressure is, whereas a PWR is going to be operating at literally 2,000 to 2,500 pounds per square inch, a little lower than 2,500 psi. The BWR is just operating essentially at the steam generator pressure, essentially is, right? So it's at a 1,100 psi, 1,200 psi. So it's actually a lot lower pressure, relatively speaking, than a PWR. So that's an important thing to do. But remember, a PWR has, has a lot of seals as well, right? Because you have all that highly pressurized reactor coolant coming outside of the reactor, going through reactor coolant pumps where you have those gland seal assemblies right along the less than AP-1000, sitting on the reactor coolant pump. You have, all sorts of peripheral systems that are moving water in and out, chemical volume charging system, right? You have thousands and thousands of tubes that the reactor coolant's running through. So I'm not so sure that the leakage aspect of this is that much different really from a PWR to BWR. BWR, yeah, has all those control rod drive mechanism penetration to the bottom, which are generally pretty self-sealing and actually sort of pressurized actually kind of nicely actually themselves, right? But I'm not so sure you generally are seeing that much difference on the leakage side on CRDMs versus the leakage challenges that we've had on PWRs, particularly on, reactor coolant pump sealing, which has been a huge has been historically a huge problem solved now, one of the Newegg 933 problems.
Yeah. So, I mean, we're going to get into some, fun illustrative stories and kind of accidents that led to some of the changes. And one of those has to do with the Browns-Ferry incident with the control rod drive mechanisms and that particularity of the boiling water reactor. But before we do, you brought up something interesting, which is, and I think this also is a partial explainer as to why there's about 2 times or 3 times as many PWRs in the world as there is BWRs. Boiling water reactors aren't great on submarines. I don't know if they were ever tried or just conceptually just made no sense, but just briefly walk us through the case against boiling water reactors on submarines or aircraft carriers for that matter.
Well, I think the first thing is that when Rickover was, first really starting this, PWRs, there was a lot more technical certainty that they're going to work and they're going to be stable than a BWR. The second reason is, of course, that one of the things we don't talk about is that in a boiling water reactor, we're bringing basically reactor coolant directly out of containment or out of the reactor compartment into the engineering spaces or the turbine spaces. And that both is highly, highly radioactive. That water itself, even if the fuel is completely intact, the oxygen atom in the water molecule gets activated by the high neutron flux of the reactor and makes a very short-lived isotope called nitrogen-17. Oxygen is usually, of course, oxygen-16, goes through one neutron absorption, goes through a beta decay, and then it emits a very, very high energy gamma photon, right? That nitrogen-17. So the steam is very, very radioactive in a boiling water reactor. And if you ever have been to a boiling water reactor, you'll notice if you look at the turbine building, inside the turbine building, you'll see the generator, and if you look at the generator, there's just been this massive wall of concrete and steel, which is literally shielding the turbine spaces from the high amount of radiation that is just generating out of that nitrogen-17. And the third issue is that as we were talking about with the sort of dual phase, that is with water and steam in the reactor core, that is that can in a submarine, you can totally imagine that when you're sloshing around, with the submarine is maneuvering around something, you can actually have that cause reactivity perturbations in the reactor core just by the water sloshing through the RPV. Versus in a PWR, the system is solid, at least in the reactor pressure vessel. There's literally only liquid water, so there's not really anything to slosh around or change the void fraction pretty dramatically, which would cause in a BWR on a ship local power peaking or something like that.
Mm-hmm. So I'm not sure if you want to move, through further iterations of BORAX or get into sort of global deployments. It is interesting, certain countries like Japan, Sweden have a real predominance of boiling water reactors. Other countries like France, I think China as well, exclusively PWRs. The Soviet Union, I think almost exclusively PWRs.
They have research BWR, right? And the RBMKs, right, which are boiling in the reactor, but Other than that,
Right.
not
So
enough.
so again, we talked about how submarines were kind of a launching point, and maybe France did nuclear submarines. Maybe that's why they chose to go PWR rather than BWR. But give me a few other reasons as to why these various
The
jurisdictions.
French. Let's start with the French, I guess. The French are weird in that, and like with many things, actually. If you've ever read about the history of the French nuclear power program, in the first generation, right, they had their own sort of UNGG reactor, and I'm sure there's some beautiful, you could say it in your beautiful French, however the French would say UNGG, but they had their own sort of like Magnox style gas cooled reactors, and actually when they sort of went down this route of standardizing on the sort of Western technology, on the American technology in the 1960s, right? Really starting on the Westinghouse and forming Framatome, which of course Framatome initially was the French American Atomic Energy Company. That's what it later stands for, and Westinghouse owned 45% of it. So Framatome itself was all dedicated exclusively initially in its history to being a licensee of Westinghouse technology. And the first sort of French pressurized water reactors that were of Framatome origin, not of Westinghouse origin, which was Fessenheim and Bouget, right? They were actually carbon copies of Beaver Valley Unit Number 1 and North Hannah Unit Number 1. But there was, people don't talk about this, but in the early 1970s, there was actually a licensing deal being put together with the French to actually standardize the General Electric Mark III BWR6 product line and actually launched that into France. It just never got anywhere. It just kind of died on the vine. But I don't think there was any sort of deliberate decision in the French, of being anti-BWR, as evidenced by the fact that they actually were interested in the early 70s actually at licensing and starting to standardize the BWR product line. The Swedish example is really interesting. I think we are jumping way ahead, right? Because we're about 20 years ahead here already. Because the Swedes did this. The Swedes obviously were building their own nuclear weapons programs in the 1950s and 60s. So had a very sophisticated nuclear program themselves, and actually originally started on the heavy water front in the early 1960s, and had these heavy water reactors that were very, very sort of safe and small, and designed not only to produce power and heat. And there was actually a reactor in Stockholm, like in downtown Stockholm, that was designed to basically provide district heat as well, using a heavy water design. They were also designed to produce weapons grade plutonium for the Swedish weapons program, which of course was sort of indicative of where Sweden was in the 50s, 60s, and 70s, and up until last year, right? Not a NATO member, right? Sort of like not non-aligned, but like sort of, going their own way. And the Swedes really did create the first, in 1968 with the creation of Aja Atom, right? The real sort of first actual non-US based commercial boiling water reactor product line that wasn't really a licensee of General Electric. Because what happened is after these BORAX experiments never go back, as you talk about the commercialization, what occurred in the United States is that you had basically 4 major reactor vendors coming into the commercial reactor space. 3 of them, Babcock and Wilcox Combustion and Westinghouse, went down the pressurized water reactor line, whereas General Electric really thought that the BWR was the winner. And so they began doing experimental BWR design first at Vallecillos, which is a research center in California. GE Nuclear at this time was headquartered in San Jose, California, where they made fuel as well. All their research sort of operations were. And then they also began building the first real large-scale commercial boiling water reactors at places like Dresden, which was the first, real 130, 180 megawatt electrical BWR. And then they began standardizing that product line into the BWR 1 through 4 product line that had, and had the same containment design to call Mark 1 containment, which really sort of began the standardized commercial offerings of the boiling water reactor product line. And then the Japanese, as you noted, really began working with GE directly, and the American architects and engineers to actually begin deploying these BWR Mark 1s, 3 and 4 and 2, right? I think actually Fukushima Daiichi Unit Number 1 was one of the first actual BWRs commercially that were going to be deployed in Japan, and that allowed Hitachi and Toshiba to actually, within Japan, commercialize the boiling water reactor product line and indigenize it as well.
So quick question there, because you mentioned standardization. And there was an antitrust action against GE, I think. As you mentioned, it was the only sort of vendor of BWRs versus you had 3 vendors for the PWRs. Did that mean, though, greater standardization? Like if you have a Babcock-Wilcox reactor, if you have a WEC reactor, Westinghouse, if you have combustion engineering, those are all different product lines. Were GE boiling water reactors more bang, similar?
You would hope that they were, but actually in some ways, the reactors are interesting. Even the RPV, even if you have a BWR Mark 1, BWR4 Mark 1, right, you could have dramatically different RPV diameters even inside that single product line.
Okay.
And the same sort of issue that we have in the general U.S. nuclear fleet exists in the BWR product line as well, where, you had all the different architects and engineers that actually built all the different systems and the building configurations and even the containment buildings very, very differently from BWR Mark 1. Like an example of this is one of the reasons why, if you think about why at Fukushima Daiichi, why the famously the emergency diesel generators were in the basement of that, is because the actual architect and engineer of Fukushima Daiichi Unit Number 1 was a Basco Services, a US-based architect and engineer who had actually just finished a BWR1 Mark 1 in BWR4 Mark 1, actually a later design in Vermont Yankee Unit Number 1. There's very few tsunamis, as you may know. And in that plant, the diesel generators were in the basement. That's a great place. You're worried about storms, worried about possibly tornadoes or severe thunderstorms. And they took that line and they just sort of translated directly over to Japan, not necessarily imagining the differences that could be happening here. So really, like any other U.S. nuclear product, the General Electric BWR product line was a mixture of the architect and engineer really designing the balance of plant and a lot of the auxiliary systems, even in some cases the containment building design, along with the NSSS vendor, in this case General Electric.
All right, so where do we go next? Are we going to learn some lessons from some incidents that helped refine the design?
I'm not so sure we've really, I think, like, do we want to talk about the recirculation pumps, which is, I think...
Yes, we do, James. We do. I can tell we do.
Yeah. So, I think one of the real lessons, as I said, is that a boiling water reactor has to actually move a huge amount of reactor coolant through the reactor pressure vessel, just recirculating it, not, turning into steam and returning as feed water. And so, one of the sort of real key distinguishing factors there's 2 ways that you can do this. The first is you can do natural circulation, which is literally allow the convective head, what we call, when water heats up, it decreases in density, which causes, in assuming there's gravity, right? It causes the lighter water to rise and the heavier, colder water to descend. And you can literally just recirculate water by just relying on the natural reactor heat to basically drive that thermal hydraulic head across the reactor water. And some of these initial very tiny reactors is one in the Netherlands, Doderwaard, Unit Number 3. There is another reactor in Humboldt Bay, Unit Number 3, which no one talks about anymore, in Eureka, California, that was a natural circulating BWR. But really, General Electric decided early on in the 50s and 60s that it made a lot of sense to do forced recirculation. That is, to use a pump to actually move this water through. What they really began to realize is that this is a great actual feature, especially if you wanted to load follow the power plant. Because what this allows you to do by just simply adjusting that pump speed, what you really can do is you can change the reactivity, that is, increase power, decrease power, of the reactor in a spatially homogeneous way. That is, if you think about how a pressurized water reactor would normally use control rods to adjust reactor power. That's not the only way. You can, of course, adjust boron as well and adjust T cold or something else. But the problem is that you actually introduce an asymmetry in the reactor. You have a control rod that's maybe halfway in at one part in the core. And that can actually cause the burnup of the fuel to burn up unevenly. Let's call it. We call it a burnup asymmetry. Whereas in a BWR, just simply by changing the amount of flow through the reactor, we can actually change the amount of power in a spatially homogeneous way. That is, in a radially and axially symmetric way, we can actually change the amount of fission that's occurring just by moving this water. That's why BWRs, hypothetically, if you wanted to, can be the best load followers, even better than combined cycle gas plants. A ABWR, a modern forced circulating BWR, can change reactor power at about 1.5% per second, right? It could really like a jet engine, faster than a jet engine, go from 60% to 100% power and back down really, really quickly, just by changing this recirc flow without any control rod movement. And that was a huge advantage. But the way that actually we did this really started to actually make the distinguishing factors of the different product lines in the BWRs. So the first way we just did it is we just had big pipes. We had big loops of pipes, maybe 6 loops, where we would take water in, have a pump, and then basically force it around. The problem with that is that you have these massive now pipes, very high diameter pipes that are outside of the reactor pressure vessel that actually pose a very large loss of coolant accident risk, right? You have huge breaks that could hypothetically occur, and you need to size your emergency core cooling systems thusly to be able to actually tolerate a break or one or two of these big loops. So starting with the BWR3 product line in GE, we began actually using jet pumps to actually move water through the reactor coolant system. And that is basically, we have what looks like we basically take a small amount of water outside of the reactor. We go to a very, very high pressure and speed, and we use that water to basically jet in and circulate a lot more mass flow in the actual reactor pressure vessel by transferring the momentum of this high-speed water into the reactor coolant, which causes a jet of water which circulates through the reactor coolant system, which really allowed us to use a lot narrower diameter piping to basically do this. And that persisted through all of the operating U.S. nuclear plants, with the exception, I believe, of 9 Mile Point Unit Number 1, which is still a BWR2. But after that, right, every other plant is a BWR3 through BWR6 with this sort of jet pump based recirculation mode. Now, the Swedes would turn this completely around, starting with their BWR75 product line, and actually add in pumps at the bottom of the reactor core that literally have a motor hanging off basically the bottom of the RPV, and they literally drive direct drives and what we call reactor turtle pumps that literally can just move the water through, which really further reduces your loss of coolant accident risk and dramatically simplifies actually this entire system. And that actually was adopted by the Americans and by the Japanese in the Advanced Boiling Water Reactor product line that we first saw built at Kashiwazaki Karya Unit 6. So, there was a real, that's, I think, one of the big evolutions that we saw also on safety systems, which you can go into as well here.
Yeah, no, I think that was important because that is a key distinguisher from the PWR line.
Yeah, exactly.
You can tell what I'm itching for. I want to hear about some near misses and what was learned and how that changed designs.
So boiling water reactors, I think, are generally, obviously, Fukushima Daiichi was a BWR, and I don't think we need to go into that. I think that's been covered ad nauseum. But, I think some of the early, there's a couple of, really early on, particularly with chemistry control, right? BWRs turned out to be particularly susceptible to a type of a corrosion mechanism called intergranular stress corrosion cracking, or IGSCC, right? And it turned out that had a lot to do with the fact that oxygen could be generated in sort of the reactor coolant system, primarily through what we call radiolysis, right? So the ability for radiation itself to split water molecules into their constituent hydrogen and oxygen components. And that sort of oxygen coupled with steam environment, right, with a relatively corrosive environment, induced a lot of IGSCC in various internals, both in the inside as well as actual welds inside the reactor coolant system products, inside the reactor coolant system itself. So we began one of the things we began doing is injecting a lot of hydrogen, just free hydrogen gas into, not that much. I mean, we're talking parts per million or parts per thousand, but basically the idea there is to basically scavenge that free oxygen and really, reduce it and make it more of a reductive rather than oxidizing environment. But I think there were a couple of major sort of challenges in the BWR product line. The first thing is that the BWRs, and a kind of advantage, the first real BWR containment design, the infamous Mark I containment, was very, very tiny, relatively speaking. The average large pressurized water reactor dry containment is about 2.5 million cubic feet of free volume. The average BWR Mark I is about 400,000 cubic feet of free volume. So they rely instead, rather than using a large amount of free space to be able to suppress the initial sort of containment pressure loads that would be associated with a large loss of coolant accident, where you break a pipe, a huge amount of water flashes into steam, and that steam is obviously exerting pressure on the containment structure. The idea of the philosophy of GE and the BWR product line really was to use a large volume of water called a suppression pool to basically take that steam and condense it directly back into water, reducing pressure, as well as having a large amount of volume of water that could be then used for the emergency core cooling system. So we have a direct sort of circulating, condensing system, which of course the PWRs have as well with the containment sump. But the idea here was to really use that water not only as sort of inventory that could be directly injected back into the reactor core, but as also a sort of energy sponge to absorb the energy that happens in the break. And starting in the 70s, their recalculation done both by the Atomic Energy Commission and by GE itself revealed that a lot of the conservative calculations utilized there were not conservative to be able to actually absorb all of the energy and the dynamic loads that would be expected in an accident. And this led to a lot of modifications that were required, including the ability in the Mark I and Mark II product line to directly vent the containment to the atmosphere, right, to prevent a catastrophic failure of the containment, because there just wasn't as much margin as had been originally calculated. And in one study done by the NRC called New Reg 1150, the actual probability of BWR containment failure in a Mark I is above 80%, right, during a large serious accident, because a PWR's containment probability is around 8%, right, in that. Now, people can argue with whether New Reg 1150, if that's actually the number, it probably is hyper conservative. I wouldn't bet that's 80% failure, but it was just dramatically less, literally tenfold less conservative in terms of those containment pressure margins on the early BWR product line than the pressurized water reactor containments were.
And not to go down the Fukushima rabbit hole too far, but that was a Mark I containment. It had this filter system on it to vent.
It did not have a filtered system.
So it just had vents, no filters.
Well, there's all sorts of issues there, but yes, it had a containment overpressure protection system, a COPS, but both US and Japanese plants do not generally have filtered containment vents. There was a lot of push by anti-nuclear people to get filtered containment vents installed, both before Fukushima, way before Fukushima, and after Fukushima. But the NRC actually refused to issue rulemaking on it because the NRC figured out that containment vents, at least in the US, were not cost effective in terms of the amount of radiation that they would prevent the public from being exposed for. Therefore, they failed the backfit there's a backfit rule in the U.S., which is is regulated by the NRC by strict cost effectiveness guidelines. There's a lot of a lot of the pro-nuclear people who don't know very much about nuclear regulation argue there's no cost effectiveness, sort of standards. There's strict cost effectiveness standards, certainly for the backfit rule. And in fact, the canonical example of this is containment filters. And it was never able to be demonstrated by the anti-nukes that it actually would pass this. So the NRC just refused to mandate it.
Okay, so just one more Fukushima thing, because this is bugging me. I heard at one point that, had there been permission to have vented some of that Mark I containment gas, that maybe there wouldn't have been an overpressurization, you wouldn't have had a hydrogen explosion. You would have still had a core melt, I guess, but you wouldn't have had release sufficient products in the same way.
It's not exactly clear that there was a catastrophic failure of the containment at Fukushima Daiichi. The actual paths of how we actually got source term out of the reactor are still actually somewhat a situation of open investigation. One of the things could have been actually what we call the dry well plug, which is literally the plug that actually sits almost like a corkscrew that sits at the top of the because unlike in a pressurized water reactor where you actually refuel inside containment, in a BWR Mark I through Mark II, you actually are opening like a lid on the top of the containment, and you're actually refueling outside of containment, right? So there's actually what we call the dry well plug, which literally screws in. I mean, it's bolted in, of course, right? And there's argument that actually we got to such a high pressure above design pressure that we basically lifted that up, and there was leakage that was occurring from the dry well into the secondary reactor building. In the U.S., unlike in Japan, the containment, the dry well valve, containment over protection system is always open to the atmosphere, and there are two burst discs in series that burst when you come close or above the design pressure of the containment that will just automatically begin venting into the atmosphere. In Japan, they had to actually open up the isolation valve in order to do it, and there was a lot of controversy about doing this, among many other things that was going on at the time during accident management that prevented arguably the opening of that isolation valve openly. But in the United States, that wouldn't be a challenge, just because our containment overprotection system is all that ISO valve is open, and it just requires two burst discs to burst, which are designed at a certain pressure to burst, and then it vents out through the plant stack.
And like very early in an accident, what's being released is mostly just steam and hydrogen, not your source term. That's the rationale for allowing that stuff to vent to the atmosphere.
Or the idea is it's there's two ideas, right? One is that it's better that we have controlled venting of the BWR containment. Remember, we should be clear, and we're kind of in a million different places here, but in a boiling water reactor, the idea would be is that you're generally actually the reason why we're not filtering, why we haven't mandated external filters, is the idea is generally that we actually are washing the fission products or the gas, like iodine-131 or coal, like the radionuclides that we're particularly interested, they're actually washing through the suppression pool. So they're sort of bubbling through, and that water bubbling is actually sequestering a good fraction of that radionuclide inventory into the RPV water, right? And then, of course, the gases that are being released ideally are noble gas, radioactive noble gases like krypton and radon, which we're not particularly worried about from a biological perspective, as well as, of course, steam and hydrogen, right? Just non-radioactive stuff to reduce pressure and therefore allow our emergency systems to better be able to inject, flow, and so on and so forth, as well as protecting the integrity of the containment building.
Okay, so I promise no more Fukushima, probably no more containment. Let's talk about, I think it's one of your favorite quasi-accidents or transients or whatever you want to call it, LaSalle 2.
Well, this is a very bizarre transient that I think sometimes demonstrates to some people the can demonstrate this sort of stability issue that we have in boiling water reactors. Right. And that in a forced circulating boiling water reactor, if you look at in a control room of a nuclear power plant of a BWR, there's what we call a power flow map that literally has, a region on one axis is reactor power and on other axis is reactor sort of coolant flow. And then what we have throughout that is, various permissible zones that we're allowed to be in. At a given rod position in reactor power, we need such and such amount of reactor coolant flow. But, that issue that we began at the start of this episode to talk about, which really was this issue of stability, we can get into unstable modes in a boiling water reactor where we have that exact sort of power oscillatory phenomenon that I was talking about. There's been multiple incidents that have happened, but in the United States, in Illinois, we had at LaSalle Unit Number 2 back in the 1980s, I believe in 1989. We had a couple of sort of regular anticipated operational occurrences that occurred. One, we tripped our recirculating pumps, so those jet pumps went down, so we're just in natural circulation. And then we actually tripped a couple of feed water heater strings, which meant that the actual pressure and the temperature of the feed water was a lot cooler than you would normally expect, which actually allowed us to get into an unstable mode in the reactor, in that sort of power flow map. And we began oscillating very, very rapidly in reactor power, oscillating from about 50% reactor power all the way up to 118% reactor power in about 2 seconds, from 50% to 100%, back and forth, back and forth, back and forth. And this gives you an idea of how, if you get out of those stable modes in the BWR, how actually quickly you can oscillate in power. And in fact, the reactor scrammed or automatically shut down on high neutron flux because the reactor was just going way, way fat, like at a higher speed. And had they actually had any sort of failure mode of that Scram mechanism at that time, later analysis by Brookhaven National Laboratory indicated that we could have gone to multiples of what the reactor design power was at peak power. So we could have been oscillating in some cases up to 2 or 3x what the thermal power design was for a second or a fraction of a second, and actually may have gotten into a place where we damaged the core, right? Just from this reactivity, this oscillatory phenomenon. And so after that, the NRC, of course, mandated that we put in what are called OPRMs, or oscillatory power range monitoring, which are constantly monitoring to see if the reactor is oscillating in power, and will automatically scram the reactor if we get into this oscillatory power mode. But, it really does give you this idea of how different the neutronics are in a PWR, how profound this negative void coefficient, which is generally and is a safety feature that we have in a U.S. nuclear power plant. But there are modes in which that negative void coefficient can cause us to get into unstable reactivity configurations in the BWR that actually do pose some significant safety challenges.
So you had said just earlier now that had the Scram mechanism not worked, meaning the control rod's not shot in from the bottom, things could have gotten a lot worse. I did sort of make a promise I'm going to break now that I wouldn't bring CANDO back into this, but we have these electromagnetically held control rods vertically above, which drop down into a low pressure calandria. So, we like those up here. If we have a station blackout, our reactors will scram all on their lonesomes. But if you're trying to force control rods up against gravity,
PWRs have that too, right? Pressurized water reactors have, gravity driven. I mean, they're held against springs, right? Electromagnetic, and they force down. That doesn't mean that you can't get what's called an anticipated transient without Scram, right? Or ATWS, right? Or ATWS, right? Because you just, as happened at Salem, I forget which Salem unit. They had, just the relay, the Scram relays welded together, and they had a ATWS. They had nothing to do with the gravity fail. I mean, once again, we have the Browns Ferry ATWS, right?
Yeah, that's what I'm trying to get at. I guess thematically, I'm just saying, like, you're having to push these control rods up rather than drop them down. That sounds like there's slightly more failure modes there. It might be more complicated. Maybe I'm way off on
I'm
that.
not sure I would. Once again, actually, there's an answer to this question which I should have done about what actually has a higher ATWS probability, the BWR or PWR. A New Reg 1150 would be a good place to start for those wanting to do the research at home about what actually the probabilistic risk analysis says on.
There are probably a few decouple guests that will pull out the regs and do the research at home. But we're that nerdy.
Between a BWR and a PWR, but there have been what was transient class, which is aptly complexly named an anticipated transient without Scram, ATWS. It happened at Browns Ferry Unit number 3 on June 28th, 1980, right? Where essentially the operators were bringing the reactor down. They brought it down already to 35% and then wanted to basically scram the reactor, shut it down for normal maintenance. This wasn't an accident situation, thank God, right? And they wanted to initiate a manual scram by just pressing the 2 buttons in the control room to scram the reactor. And they pressed the button and the reactor didn't scram. And in fact, on the control rod cartogram, the sort of, control rod indicators, right, what they realize is that, when you scram the reactor, of course, the reactor is supposed to fully shut down. All control rods are supposed to go in, I think, in 2 seconds, I think is what is generally, I think, the regulatory required time for control rod timing. And what they recognize is that when they press the button, they had 185 control rods that should have gone fully into the core. Only 76 rods were still not in the core fully, and the reactor was still critical. And then they pressed the buttons again, and 59 control rods remained partially withdrawn. And then they pressed the button again, and 47 control rods still remained in. And then it took literally about 15 minutes and 4 scram signals initiating for all of the rods to get into the core. And now this wasn't a big deal. The reactor was fine. Everything was working fine at the plant. But had we had a serious accident or transient occurring that required the reactor to promptly shut down, this could have been quite a serious incident. And it turned out that the issue, how much do you want me to go into actually why this happened? I mean, like, first of all, let me just say, I love boiling water reactors. I feel like we're like shitting on them all the time right now. Like, by talking about these transients, like BWRs are the best, and like they're the best water reactors, right? Like, so like I prefer them over PWRs. I'm not trying to say like ATWSs happen in PWRs. I don't want to say that. And like we're giving these highlights. I think, I think I was having dinner with Nick Turan last week, and I think one of the things that Nick and I were talking about a little bit is that some of the, I mean, I'm not that old, but like some people in the, or in the startup space or in the new space in this industry, and, you have this sort of Twitter community of nuclear people, which, is, anyway, sometimes there's a hubris of people who are not, don't necessarily appreciate the serious, I don't want to call them near misses. That's a little dramatic, but the serious challenges that we had in the operating fleet 30 or 40 or 50 years ago, and the immense amount of knowledge that has been acquired over 50 years of operating BWRs and PWRs. And there's a sort of arrogance that it always will be this safe. And I think that obviously operating nuclear power plants are the safest form of energy, bar none. But a lot of the reason why we are so safe and so reliable is that we've actually had these real world accidents and near accidents that have occurred, and we built regulations and systems that have, directly addressed those safety challenges. Right. So in this ATWS sort of situation, the reason what it occurred, how much you want me to go into how a hydraulic accumulator works in a
Yeah. Don't go
I don't
deep,
think
but
you want me to go to how a Scram, how the hydraulic pistons work in the bottom of it, and how you could plug the basically what happened is there's crud that was basically
crud.
in a BWR, basically the bottom of it in a Scram, they have nitrogen accumulators at very high pressure, right? And they have a water piston, and the nitrogen displaces the water and basically pushes the piston up and pushes the control rod into the reactor. And it turned out the headers that basically had that water, that allowed that water to move out and the nitrogen gas to displace it, were clogged, right? And that basically, water is an incompressible fluid, right? So when you got this nitrogen gas like trying to come up when the Scram solenoids opened, right? So the solenoids, open up, flood the nitrogen gas, which basically should force the control rod piston up, right? That water couldn't move out, so it got stuck. And literally they had to redepress and, basically repressurize those nitrogen accumulators over and over again, like a clogged toilet, to basically jam out the junk to basically allow the water to move in and to do that. But after that, the NRC, of course, mandated something called SLICS, or Standby Liquid Control System, which basically says that we have to have this ability to inject liquid boric acid directly into the boiling water reactor, right? Which generally would probably ruin or very seriously damage the internals of a BWR, in order to have an alternative mechanism of scramming a BWR, right, to mitigate the ATWS, the ATWS risk, right? Just because after this accident. And one of the controversies brewing right now in the BWRX 200 is whether we actually need that standby liquid control system, given how much increase in reliability we now have on those control rod drives.
Right. Lessons learned, as you said. Okay, well, as you're mentioning, we're not here to trash BWRs. You want to talk about the absolute best water reactor, I think. The crowning achievement of humanity when it comes to deploying a nuclear reactor quickly, certainly on a per megawatt basis.
I don't know if they're on a per megawatt basis. I'm not sure of exactly any BWR that's been faster than any nuclear power plant. Even the Chinese have not beat Kashiwazaki Karya Unit Number 6, right? Which really only had about 38 months of nuclear construction. It's a 1.35 gigawatt, certainly not a small modular reactor. It's a very large modular reactor. But I would say the ABWR is sort of a really, really beautiful design process that occurred. It was starting in the late 70s, actually sponsored by Tokyo Electric Power Company, TEPCO, and run by General Electric. GE brought in, Hitachi, Toshiba, GE, of course, and the Swedes and the Italians all into a single design group to figure out what is the best sort of operating experience, what is the best design elements that we can take out of the Swedish and US nuclear and Japanese nuclear fleet. And they began actually a design process to create the Advanced Boiling Water Reactor, which was going to be the first generation 3, the first and the best, obviously, generation 3 nuclear power plant design. And out of that, they took some of the best elements out of the U.S. fleet, particularly on steam dryer design, right? They took a lot, and fuel. They took the best of the Swedish sort of nuclear power fleet and really did these reactor internal pumps, right? Eliminating those jet recirculation loops. They took the Mark II containment design out of the U.S. and out of the Japan and improved it, and built a really rationally designed, with GE, Hitachi, and Toshiba as the vendors, really rationally designed new nuclear power plant design. And that's the ABWR, the Advanced Boiling Water Reactor, or as I affectionately call it, the absolute best water reactor, right? And that design, building in 1992, was able to have nuclear construction done in 38 months in Japan at Kashiwazaki Karya Unit Number 6. And we basically built a 1.35 gigawatt plant in less than 4 years of nuclear construction, which is extraordinary. And we continuously did that in Japan at Kashiwazaki Karya Unit 7, Shimane Unit, the Shimane units, as well as 2 others, and then in Taiwan as well at Lungmen nuclear power plant. And these really, in my mind, the world would be a much better place if, rather than Vogtle Unit 3 and Unit 4 being a AP-1000, it would be an ABWR, right? Because the design in particular that Hitachi and Toshiba did, not just on designing a really good sort of NSSS design and so on and so forth, but a fantastic constructability, aspect. Constructability was part of every part of the design process that was done. And dramatic simplifications in instrumentation and control that was enabled by real sort of forward-thinking regulatory changes starting at the US NRC and at the Japanese regulator in the 1980s, which allowed us to really simplify a lot of cable pulling, a lot of the cable trays, a lot of the critical path elements that really have delayed nuclear power plants historically.
So Vogtle 3 and 4 would not have been first of a kinds. They could have benefited from the building experience in Japan.
Well, it's just that what my whole question always is, and Okuluto, it's not just, the real criminals here, of course, are the French as normal, and the French, really screwed the Finns a lot, because Okuluto Unit number 3 was actually to the last minute going to be an ABWR. Of course, the two Okuluto Unit 1 and Unit 2 are Scandinavian. They're boiling water reactors of Asia Atom vintage, right? And the French underbid for the EPR, the ABWR, and they lost out. It's a great lesson. And I think we should all pause here and ask this question here. Here the Japanese, had GE, Hitachi, and Toshiba all offering ABWRs in the United States, fully licensed by the NRC. It was actually the first reactor ever licensed or gotten a design certification under the Part 52 process in 1994. The big question that we should ask ourselves is, hey, this reactor was built in 38 months. And by the way, 40% cheaper on the first of a kind reactor than the seventh of a kind BWR-5 Mark II that was being built in Japan continuously. So it was not only faster, but dramatically cheaper. In real world, it beat the seventh of a kind on its first of a kind. Given that data, what sort of decision making, what is the lessons learned that we can have as a community as to why we just didn't choose the ABWR? There's certainly no regulatory reason why it couldn't be chosen. In fact, there was 2 South Texas Project Unit 3 and Unit 4 got licenses to build ABWRs, but never built. But we're seeing the exact same phenomenon now, where we're taking proven designs that have a track record. Obviously, ABWRs is still just got recertified. 2021 is still the best reactor. I still would look at it. It has a great supply chain with Mitsubishi Heavy Industries and Hitachi, right, who have been continuously doing shipbuilding and everything else to build that modular supply chain. We're doing the exact same thing right now, where we're saying, oh, we should just build an entirely new, SMR or whatever, right, that has no actual lessons learned, no track record, rather than we're repeating the exact same error that was made in the first nuclear renaissance, which was not choosing a reactor design that actually did the thing that everyone is saying is impossible, which is building a reactor in 3 years and 8 months of nuclear construction, and 40% cheaper on the FOAC than on the NOAC.
Yeah, I mean, I think I've made it abundantly clear my technology choice, nationalistic technology choice for Darlington. But I have to say, like a single ABWR, which would have more output than 4 BWRX 300s, which are first of a kind and have a lot of
ABWR to 1,500 megawatts, relatively trivially, right? And then you have, essentially, you have 5 BWRX 300s in the single plant,
which historically have been built in 38 months and,
have actually been built in the real world in 30. And are extremely mature, backed up by a very, very, very mature technological supplier. So we should all be asking the question here, why, what are we doing again here? And we did this mistake in the first nuclear renaissance with the AP-1000, in my opinion. Obviously we can't cry over spilt milk. It's no longer a mistake. But I do think that had Southern Company or SCANA built an ABWR rather than a AP-1000, those builds would have looked very much differently, just because the design was complete. As evidenced by the fact the plants were built and operating, right?
Right,
And
right.
had hit it out of the ballpark. Anyway, you know, yeah.
But I mean, this does, I think, take us into interesting territory, and we are on the final countdown, dear listeners. But I do want to hit on passive safety and natural circulation. That was, I think, one of the big selling points, and maybe why the AP-1000 was selected. It's the Advanced Passive 1,000 megawatt reactor, and the ABWR was still using a lot of active systems. So the ESBWR was the next design iteration.
We should pause right there and just say one of the arguments, and I'm going to commit a mortal probabilistic risk analysis sin right now, which is actually comparing unlike PRA methodologies from one to the other. But if you were to believe GE Hitachi's PRA methodology,
probabilistic risk assessment.
So they could estimate something called the core damage frequency, which is an interesting number that exists. Ostensibly, actually, the core damage frequency of a ABWR should be lower than the AP-1000. So actually, I would not argue that an ABWR is less safe than an AP-1000.
Okay,
That's
a very diplomatic good point.
I wouldn't argue it's more safe, but there's no reason to think that an ABWR is less safe than an AP-1000.
Okay, so perfectly good design, fastest build times perhaps ever. Why the ESBWR? Is that to at least get the kind of marketing of being?
I don't know. You should ask what Hitachi. I have no idea what the point.
All right.
No one's ever. I don't think anyone's gonna ever build an ESBWR. Like an ESBWR, like the BWRX 300 is a natural circulation 1500 megawatt. We have never built a natural circulation core. I think the biggest natural circulation boiling water reactor ever built is around 200 megawatts thermal. Already going up to the BWRX 300, that's going to be 900 megawatts thermal to 1,000 megawatts thermal. A ESBWR is a monster at 4,500 megawatts thermal, give or take. I don't remember the exact number, but about 4,500, maybe a little bit north of that. And the idea, I know people who are very wary of the stability issues. With a pump, ultimately, if you get into an unstable zone, or if the thermal hydraulics work slightly differently than your computer modeling indicates, well, it's a pump. You can just pump more water, pump less water, pump water at different times, at different speeds. It's not the end of the world. When you're in natural circulation, Mother Nature is in the driver's seat, right? Sir Isaac Newton's in the driver's seat. And at that point, you really can't tell Mother Nature how to change your thermal hydraulic head. So once again, GE has expended millions and millions of dollars and decades of researching the core stability issues that could possibly arise in a boiling water reactor. In the ESBWR, the NRC double-checked it, so did the Advisory Committee on Reactor Safeguards. Everyone approved it, says it's going to be stable. But there are people who I know who are very sophisticated thermal hydraulicists who argue, ultimately, if we were going to build an ESBWR, that would keep him up a little bit at night until, obviously, the first one turns on. Right? And the ESBWR is fully passive, as you noted. The ABWR can, for a couple hours, deal without power using a system called RCCI, or reactor core isolation cooling, which is basically a steam turbine that takes the steam out of the reactor and spins a turbine that pumps water back into the core. You could actually, mitigate a station blackout scenario with a RCCI, especially with a turbine lubricated pump from Clyde's Union that doesn't require any power even to do control. And there are obviously very easy ways actually to make as evidenced by the ESBWR, really easy to make a BWR not require any power for decay heat removal, much simpler than the PWR, by just basically doing what's called an isolation condenser, where you basically take the steam, have the steam go into a big radiator that is in a big pool of water. That steam condenses back into water, and that water just returns back to the reactor pressure vessel. And you can run that forever, hypothetically. And that's what the ESBWR does. I think a next generation ABWR would have a slight tweak, probably with an isolation condenser on it, which would give that extra passive safety. But it's not clear that really The ABWR has 3 emergency diesel generators that are physically segregated from themselves and a backup combustion jet engine, gas turbine, right? And this RIC-C system. So the probability that you're going to really get into that such a quadruple failure mode plus RIC-C failure and not be able to mitigate it with flex or something like that, I think is highly improbable.
Right. And then the move, we've touched on this a little bit with Karush, but the move to passive circulation, particularly with an SMR, means that you're having a very large reactor pressure vessel and larger civils and things like that. Which...
It's complicated, right? Because like on a BWRX 300, the RPV is much narrower, right? It's much narrower. It's like much more like the size of a steam generator, essentially, than a classic RPV. ESBWR, the RPV is a monster, right? It is really a monster. Anyway, I think I've realized we've got going for a while now here.
Yes, we have. Okay. Well, I think that was a great backgrounder and a great place to end. And we'll pick up maybe talking some more about uprates in the future, or
let's talk more about uprates.
All right. Sounds good, James. Thanks for coming back on.